on the ground on foundation of manifold type game theory, which is the basic tool that will be used here in terms of modeling, prediction, analytics about the nowcasting and the forecasting aspect of the spread of the virus. So the basic idea will be based on game theory. So the people I would like to acknowledge and who contributed to this work are Dr. Julian Barrio Commerce and Dr. Sarah Eden Chotri and my previous and former PhD students, Dr. Jiang Gao and Dr. Yide Xu, and former postdocs and collaborators were Dr. Masa Ndok and Dr. Mikhail Marquez, and former PhD advisors and the long-run collaborators in France, in the US, in Switzerland, as well as in Asia. So this is also sponsored by the Center on Stability on Turbulence, and as I said, by the US Air Force on the foundation of manifold type game theory. Um, so the problem we address here is to understand the spread of the virus, starting from one country and then moving out across other countries because of international connectivity, flight, boats, and so on. And then once it's in another country, then because of mobility, via ground transportation, interconnection between cities, so it spreads across cities, and then inside a city because of public transportation or because of the mobility, local spread at the hotspots. So we'll be trying to model this through the map and data-driven context, and then we'll take the epidemiology model, which will be extended actually to capture more states, more internal states. So in total, we'll have 17 states, including the tested positive and the untested who are positive as well. And this will be an estimation from the model. And the number of hospitalized will be part of the model so that we can plan in advance on a weekly basis, so that the point of care and that hospitals, number of people who are in intensive care and resources will be more allocated for those who are in need and so on. And then the second block of my talk will be on the control of the basic SIRT model, which is successible infected, recovery, or death, in which we are going to introduce age structure and a spatial structure. Age structure because it looks like from the data, although the data are not at a level, but in some countries they are more. The death rate turns out to be a function of the age, and increasing function with age. But the structure, there's a specific structure depending on the country. So that need to be incorporated, and this is why we suggest to introduce the age structure in the model. And then a special structure because depending on the country, the decision made by the authorities are not the same, and the social and socio-economic interaction in the countries are different. So therefore, the spatial structure plays a role in the propagation of the virus. So this is how we introduce spatial and of course, we're going to introduce other things like vulnerable people, comorbidities, and the in terms of the propagation of virus. Now, my last block of message here concerns the data-driven modeling, where we include decision making about the to contain the virus, one thing, and decision making and incentives to protect the economy and to support people who are in need, who cannot work, and people, in particular those with low income. And also, so how should we balance the budget? How should we schedule the confinement in many countries and so on? So this is the agenda. And you can see here that, so we start around this area in Wuhan in China. And then because of international flight and the national connectivity. The virus spread, into Asia, other part of Asia, and then to Europe, and then to the US, and then to Africa, and Australia, and so on. So now it's worldwide, and a couple of days ago it was about 4.7 million. Um, now it's much more worldwide infected. And then here you could see the color indicates the infections. Now, initially, you will realize that actually only few countries were infected, and progressively, this is the top 15 countries. And this is, for example, China, and then this is US, and this is mostly European countries. Now, the spread is continuing, but now it's almost at the local, at the community level, at the city level, at the country level, no more than international ones, because of the international flight restrictions and so. And so we consider two branches, two main areas: the pandemic aspect and the economic aspect, and both are important actually, and they play an important role in the sense that if you want to contain a virus, we have to make proper decision at the early stage, and uh, and uh, and uh, and if those decisions are somehow restrictive, and if they take longer time, means couple of months, 3 months now, then they start creating more economic consequences. The more it's longer, the more there will be consequences. So we have the pandemic consequences. We want to avoid them, and we want to avoid as much as possible the economic consequences. And in terms of economy, we look at the the physical, the taxes, and the the incentives that the authority have made in order to support companies, support employment, and so on, and the support in particular the most vulnerable people. And in terms of firms, so they have to make a decision about protecting their employees, reduce the number of infection at work, number of working hours per week. So they need to plan those things. And for individuals, well, they have to decide if they continue to work, if they could do online work or offline, on-site work, if they could reduce the work hours on-site. And of course, they have to plan on food if it's not provided by the state. So it means that at some point, some family member have to go out, and that's somehow when you go out, you have infection through surface contact, infection through coughing and sneezing. And this is one of the aspects that we try to model here to compute the probability of getting exposed, which plays a key role in the infection propagation. Now, the quantity of interest are, the number of deaths, number of deaths to be minimized by authority, and of course, total number of deaths is of interest. And we want to reduce this number as small as possible, right? Number of hospitalized, because the resources are limited at the hospital, so we need to plan in advance. We need to increase the capacity of the hospital, increase, in terms of medical supply, in terms of ICU, intensive care units, in terms of respiratory machines, and so on. And we need to estimate the total number of people who have been infected, tested positive or not, because then we can plan somehow some of them will be hospitalized. So it's kind of a prediction that we can incorporate into the model. And in terms of economic losses, so what will be loss depending on the measure taken by the authority? If it does take 2 months, it's not the same as it takes 6 months or so. And then the comparison between, for example, the number of deaths predicted by the model versus the number of regular deaths in the past years. So in a semester basis, and then say, okay, looks like this year it is going to be more or less or similar. Right? So for this, we will use a data-driven meaningful type game theory. Meaningful type game theory, meaningful first game theory because there is decision making involved on it, and meaningful type game theory because you are risk awareness involved on it, and data-driven because the data provided by the country will be taken into consideration here. And that these are existing models going back to Brown and Bernoulli in the 17th century, 17th and 18th century, and where we actually extend those to capture some of the things that are going on for the COVID-19. There are some key differences between the one that are proposed here, our model, with the existing classical models, which can be extended, but not always done in a proper way. So the model of three-state is basic and everyone can understand it and how it works. But if you run an ODE, it's not the same as an SD. So we can do individual agent-based with decision-making on it. So we do on markup chain, the three-state, and that's predict better. But actually, that's extremely slow. That's why people take this one. There's three-state, but which is an advantage, but it's also an inconvenience because if you want to know the number of hospitalized, it's not capturing those markers. So you can extend to four-state to include exposed people, five-state to include remove to be split into recovered and death, and special structure, age structure, and so on. So we have 17 internal state. I'll show you the diagram in the next slide. In particular, it incorporates age of the agent, the gender, because the gender actually appears in some of the data that there is a significant difference, at least in some countries. So we need to look at this more carefully. The height of the person in order to compute the probability of getting exposed when you are standing up. The pre-existing health condition is one of the key things because of the comorbidities. It is coupled with COVID-19. Some of them might be severe condition. Family size at home. I mean, family size, household numbers, total house numbers, and the average revenue for family side, which is what we call economic status. The testing strategy of the country decided by the authority, the decision making for individual, for firms, and for authorities, and the number of people who are positive to COVID-19 but who have not been tested as an estimation, and the data driven. So these are only some of the features that are incorporated in our model, but not in the other model. Therefore, we might come up with some extra information because of the data structure we are using. So now, control aspects. Before introducing the control aspect, I will explain the basic SIR model. So S is for successible, I for infected, R for recovered, and D for death. Now, ST denotes the thunder variable. So it's a function of possession, which is X, H, which is Z, economic status, the average income, for example, for family size, which is E, and T is for time. Now, this successible person is located at X, and it can meet an infected person who is at X prime, and it will meet with a certain rate, and the kernel of interaction is given by beta here, and this depends on how other people, infected people, are around that position or so. So, for example, if the distance between X and X prime is small, then there is a probability of being exposed by an infected person in X prime. Otherwise, beta will be small or zero, then the probability of getting exposed is very small because it will be only the surface contact or so. Now, this will be the evolution of the successible. As you see, it's going to decrease as A is positive, S is positive, beta is positive. Now, it's going to the one that are leaving us, they leave us and they are going to means they will be infected. So if they are going to be infected, then this will be added into the IPOP. So that's why you have the plus sign and the minus sign here. And then some people who are infected will be recovered with the rate gamma, and some other people will die with the rate delta. Now, what is important here is the delta is a function of the age. So, which is somehow what is observed in the data set. It means that the more, for example, when you increase Z, then the delta rate will be higher. um, in many countries. And of course, it depends on the country, it depends on the economic status, although in the data set, that part is not clear. Some people would hire rate of more death. You might explain this through other parameters like the probability of getting exposed initially. We start from high-class travelers, and progressively it's at the community spread. So there are some disparities. It doesn't explain all the parameters of the death rate, but it does explain at least the age part and some other and, and it's about the contact rate. So what is important is to explain the contact rate. The model does not really tell you, does not explain the depth. It's explaining you the exposition, the probability of getting exposed, and then the probability of getting infected. Although the data provided by the countries are not capturing not that accurately, because actually testing, they are not testing enough, or they need to do the more efficient testing. For example, randomized, pooling by sectors, and that's how you can move fast. The session already about the model earlier. I will go fast, and that is model 2 is here, and model 2 is extending this, and now we do control version here. We do meaningful game version here. We do meaningful type game version here. With the risk awareness part of it, with the variance of the decision making involved on it. Here is references on meaningful games. These ones are references on meaningful type games, and this is the diagram on meaningful type games that will be used as a tool to solve the problem. And then now the data-driven model, as I said, so we'll have the evolution of the spread across the world and worldwide. Authorities will decide on migration rules, lockdown, and incentives. And objective for the authorities to reduce the number of deaths and also to balance with the economic losses depending on the country. And firms can look at the production of essential, moderate essential, and less essential goods, and they decide on the total working hours, as I said, and the subject to constraint. And their goal is to reduce number of infected employees and maximize profit. For individual, it's a balance again between economy and pandemic. And in terms of economy, the working hours reflect some benefit. And if you go outside for the food, it reflects some other benefit. But then there's a cost because you might be exposed and so on. And in terms of pandemic, of course, you want to avoid the places where there are infected people. The problem is you don't know where are the infected people. Now, all this population dynamics is given by M, and M will evolve over time. It's divided into L, which is location. Location is split down into countries, cities, and then areas of the city. Now, in the area of the city L3, there is a position of the agent X1, X2, H, which is three-dimensional thing. H is the hive, you could just remove it. X1, X2 is typically geographical coordinate or so. And S is the infection status, and here comes our epidemiological part of the model, which is suggestible, exposed testing, positive testing, negative testing, false positive, false negative, and isolation at home, at hotel, at point of care, hospitalized, and so on, age. And then C is for pre-existing condition. It's involved, mild conditions like MD, or people with severe disease, chronic disease, diabetes, hypertension, or mixed syllable for high blood pressure, cancer, and so on. It's include also the gender, the height, the family size, the economic wealth, income per family size, and the T is for type. Now, the 17 diagrams are highlighted here. And if you remove all this branch, and then you are left with only suggestible, and then exposed testing, and all this, we pull it as in the infected early infection, pre-infection setup boxes, and then you have recovered. So you'll have suggestible, infected, recovered, right? So
So the D will be 3 states, we include deaf, and the SIRD will be with 4 states. So our model include those, prior models, and in fact, and it's extend them, including spatial structure and so on. So this is the ODE with the age and so on. So the drift given by the 17 internal states that we plot, and you could see here the evolution of the population. So one important thing is that this model for some range of parameters can capture second wave, means there is a first wave here, and then they start continuing, and then a second wave. And this type of behavior cannot be observed using the basic SIR, because in the basic SIR it goes up and then goes down. There is no way to go up again because of the basic ODE with the steady state condition, right? So the dynamics in the general context is summarized in this slide, and this is the Kolmogorov equation, where the authority decide on eta 1, which is international flight, eta 2, which is intercity flight, intercity flight or intercity mobility, ground transportation, and eta 3 is intracity, inside the city, from one area of the city to another. So authority can decide partial lockdown inside the city, or partial specific lockdown of a city, or global lockdown of the country from outside, from international connectivity side. And local mobility in RL3 is given here, and it might include actually mobility with divergence and Laplacian terms, and the step size when we walk, and the death rates is given by DT, and two constraints: number of hospitalized not to exceed the resources available at the hospital, and actually this is a planning, so it means that we need to extend the capacity of the hospital if we see that the number of hospitalized start getting close to the resources that are the number of beds, number of ICUs, number of nurses, and so. Same for testing. We need to increase the capacity of the testing and to do a plan advance that. So, and in terms of interaction, so if you want to model physical distancing, for example, distance between X and S prime to be less than 2 meters, 1.5 or 2 meters or so, then beta is reduction. So if the distance is very large, then beta is 0 or small for the general context, and then it doesn't affect you. You will not be exposed, right? But actually, the infectious is more. We have more states here. Is equal to the one who are asymptomatic, passive state, active, and but not tested. The one who are tested positive, the one who are tested positive and who are at home, quarantine at home, and quarantine at the point of care, or quarantine at the hotel, and the one who are tested positive and who are hospitalized. All right, all those are infectious, and you add them here, then you multiply beta convolution, with the kernel here, and then this is probability for S. And then we get our model. We start from the data. We get the parameter of the model, and then we plug that into the model. We get a data-driven model, and then we optimize, and then we make a decision. Once you make the decision, it goes back and get in the data. So then you can go for verification, validation, and then you can calibrate the model and keep making new decisions and optimize again and so on. So it's a prediction correction based on what is observed. Data set is available online. There is the website, and the measurement is like 5 different input for each country, and we have 195 countries. And the optimization step to get the parameters is given here, and the data-driven model is given here. And on top of this, now we do the control and optimization perspective, and then return after the decision making, best decision making. These are the implementations, and the data are given online from different sources actually. And for each population, for each country, we look at the population in details, and international connectivity, local lockdown, local responses, economic situations from different sources as well, comorbidity data from different sources as well. And this was the state as of March 30. This is the local spread, how the mobility goes. So this is the mobility data. This is the initial infection status. And then when we propagate, it becomes something like this after 1 month or so. And this is the simulation for India. You can see that the data-driven model capture what is going on. So this is the power of the model is that it can capture some of the data input, and in some countries it doesn't. So it might say that there is something wrong going on. So it's able to detect some behavior and a specific shape that so that you can do some planning. This is for Russia. Again, the model is perfectly fitting with the data set. Um, this is the log scale version. That's why it looks like concave. This is for Spain, and this is when you optimize. When you optimize with optimal control, it goes down much faster than what is observed. It means they are not implementing the optimal. All right. So I have shown you the integrated pandemic version of economic control aspect, data-driven aspect, and they spread across several countries. Decision making is part of our model, and there are other 66 countries that are on. Here is for Argentina, for example, where you could see that it captures very well. Here is for Bolivia, it captures somehow at a certain scale. Here is for Brazil, where the epidemic is still at the beginning. The data set captures the model capture actually the recent behavior observed in the country. This is for Chile. Actually, it captures as well. This is for Colombia, and the model perfectly fits with what is observed, including a prediction step for 10 days. And actually, it does very well for 1 month as well. This is for Ecuador, where the data again capture, the model capture what is going on in that country. This is for Paraguay. This is for Peru. This is for Uruguay. This is for Venezuela. This is for Cuba. This is for Guatemala. This is for Haiti. This is for Mexico. This is for Bangladesh. This is for India. This is for Indonesia. This is for South Korea. This is for Malaysia. This is for Pakistan. This is for UAE and the United Arab Emirates. This is for Germany and Europe. This is for Italy. This is for Russia. This is for Spain again. This is a sample for selected countries in Africa. This is for selected countries in the east of Africa. And this is for selected countries in the west of Africa. And this is other selected countries in the south of Africa. And this is the data driven, how it's evolved across time. This is for Algeria, this is for Angola, this is for Botswana, this is for Benin, this is for Burkina Faso, this is for Burundi, this is for Cameroon, this is for Chad, this is for Djibouti, this is for Egypt, this is for Eritrea, this is for Eswatini, Swaziland, this is for Ethiopia, this is for Gabon, this is for Ghana, this is for Guinea, this is for Guinea-Bissau, the second one, this is for Kenya, this is for Liberia, this is for Libya, this is for Madagascar, this is for Malawi, and this is for Mali, this is for Mauritania, this is for Mauritius, this is for Morocco, this is for Mozambique, this is for Namibia, this is for Niger, this is for Nigeria, this is for Rwanda, this is for Senegal, this is for Seychelles, this is for Somalia, and this is for South Africa, this is for Sudan, this is for Togo, this is for Tunisia, this is for Uganda, this is for Zambia, this is for Zimbabwe. So many other countries in the slides here, but we have done much more. So here we have seen 66 countries, and you can see that the model is actually capturing that. Now, what is the next step? Well, we want to do more, planning, more decision making, so that we can make more impact in containing the virus, as well as in reducing the economic consequences, so that people can return at work, or can manage better the situation that is going on. Thank you very much. Thanks for your attention. If you have any question and comment, I will be happy to